Good day. I am Bleslie Gapuzan, and my co-reporters are Jose Billan, Stephen Christian Cabatingan, Junaleen Castigator, Novelyn Casumpang, Monriel Esparrago, Leizel Mae Fontanilla, Kledd Goles, and Sheila Marie Manzano. So today we will discuss about the transmission line calculations. So before that, what is transmission line? So in electrical engineering, a transmission line is a specialized cable or other structure designed to conduct electromagnetic waves in a contained manner. So the term applies when the conductors are long enough that the wave nature of the transmission must be taken into account. So a transmission line is a system of conductors that transfer signals from one place to another. So the rising and falling of waves moves the buoy-like structure, creating mechanical energy which is converted into electricity and transmitted to shore over the submerged transmission line. So transmission lines are made up of conductors having a uniform cross-section along the line. So transmission lines physically integrated the output of generating plants and requirements of customers by for the flow, providing pathways for the flow of energy among the various circuits in an electric power system. So we consider a transmission line to have a sending end and a receiving end, and to have a series resistance and inductance and a shunt capacitance and conductance as a primary parameters. So in addition, we classify transmission lines as short, medium, and long. So next slide, we will discuss what are the short, medium, and long transmission lines.
So, now that we're familiar with the transmission line, let us proceed to the background of the transmission line, which is the transmission line representation. So, in general, the differential equation mentioned are difficult to solve in the time domain due to the convolution integral. But in the frequency domain, these equations become simpler and their solutions are known, which means to say that the transmission line can be represented by a cascade of PI circuit to facilitate performance calculations relating to the transmission line, in which the transmission line is approximated as a series parallel interconnection of relevant parameters. Now we have three representation of transmission line, which is the number 1, short transmission line, number 2, medium length transmission line, and lastly, number 3, the long transmission line. First, we're gonna tackle about the short transmission line. A short transmission line for which the shunt effects may be neglected is represented by a lump resistance in series with a lump inductance. Short transmission line have length lesser than 80 kilometers, which means within 50 miles, and operate on a voltage level lower than 20 kilovolts. Furthermore, in short transmission line, capacitance effect are significant and we can neglect the effect, which means to say that their performance depends upon the resistance and the inductance of the line.
Medium length transmission. A medium length line is represented by lump shunt capacitor located at predetermined points along an RL series circuit. Its transmission lines having length between 80 km and 240 km are medium transmission lines. They operate between 20 kilovolts and 100 kilovolts. As the length increases above 80 km, the capacitive effect becomes quite significant. Long transmission line. Long transmission line is represented by uniformly distributed parameters. A long transmission line is defined as a transmission line with an effective length more than 250 kilometers or 150 miles. Unlike short transmission line and medium transmission lines, it is no longer reasonable to assume that the line parameters are lumped. It operates voltages above 100 kilovolts.
Short transmission line. A transmission line is classified as short line if its length does not exceed 15 miles or it is less than 80 kilometers. The short transmission line is represented by the lump parameters R and L. It will be shown in figure 4:1. We will notice there that R is the resistance voltage per phase and L is the inductance voltage per phase of the entire line. The line also is shown to have two ends, the sending end and the receiving end at the load. Quantities of significance are the voltage regulation and efficiency of transmission. These quantities are defined as follows for lines of all lengths. Percent voltage regulation is equals to the absolute value of receiving end voltage of no load minus the receiving end voltage of load over to the absolute value of receiving end voltage of load multiplied by 100. To compute the efficiency of transmission, it is equals to the ratio of receiving end power or PR over the sending end power or PS.
This is the equivalent circuit of short transmission line. It consists of resistance and inductance. So, these are the series impedance of this circuit. So here we have the sending end voltage and on the other side is the receiving end voltage. So this voltage releases the current, which is the sending end current, and in this voltage it takes the receiving end voltage current. So as we can see that this is on series, so which means that the sending end current and the receiving end currents are both equal. And also this reactance and resistance and inductance are the lump parameters on this transmission line.
Let us now proceed to the medium-length transmission line. In this transmission line, the shunt effect due to the line capacitance is not negligible. Two representations for such a line are shown in figure 4.2 and 4.3. They are known as the nominal 2 circuit and the nominal T circuit of the transmission line respectively. The figures also show the phasor diagrams for lagging power factor conditions. These diagrams are of help in understanding the mutual relationships between currents and voltages along the line.
Nominal T model of transmission line. In a nominal T model of a medium transmission line, the series impedance is divided into two equal parts, while the shunt admittance is concentrated at the center of the line. In a nominal T model of transmission line, the whole shunt capacitance of line is assumed to be lumped at the middle of the line. The half of the line resistance and reactance is assumed at either side of the shunt capacitance as shown in the figure below. Due to such modeling of line, capacitive charging current is flowing through half of the transmission line. Mind that it is not the case in end condenser method. In end condenser method, capacitive charging current flows through the entire line as shunt capacitance is assumed to be lumped at the receiving end. Nominal pi model of a transmission line, of a medium transmission line. In the nominal pi model of a medium transmission line, the series of impedance of the line is concentrated at the center and half of each capacitance is placed at the center of the line. In nominal pi method, the shunt capacitance of each line, i.e. phase to neutral, is divided into two equal parts. One part is lumped at the sending end while the other is lumped at the receiving end.
Long transmission line. The parameters of a long line are considered to be distributed over entire length of line. One phase with the true neutral of a long line of length L1 is shown in figure 4.4. The voltage V at any point along this line is given by this second derivative is equal to y squared V, where y is equal to square root of yz. Y is the shunt admittance per unit length of the line. Z is the series impedance per unit length, and y is known as the propagation constant. A solution to 4.3 is V is equal to 1 of V sub r quantity e to the yx plus e to the negative yx plus 1 of I sub r times z sub t quantity e to the yx minus e to the negative yx.
So let us consider that for distance x from the transmission line from the receiving end Vr to its incremental length of dx, the voltage is increased to V plus dV, and here the voltage is V. So the net impedance we take to be Z into dx, and the net admittance we are taking to be Y into dx. So the equation that will be formed due to this assumption is dvx is equals to ix z dx. So we can form an equation dvx over dx is equals to zlx. Similarly, the incremental current dix is equals to vxy dx. So the second equation we can form dix over dx is equals to y vx. This formula comes from V is equals to I times Z, and current is equals to voltage times admittance, which is the I is equals to V times Y. So these are the basic formulas through which we have formed this equation.
So the equation 4.4 and 4.5 may be expressed in terms of hyperbolic function, as the voltage V is equal to V sub r cos yx plus I sub r since yx, and the current I is equals to V sub r since yx over z sub e plus I sub r cos yx. And since V is equal to the voltage at the sending end and I is equal to the current at the sending end, at x is equal to the length. So the equation 4.6 and 4.7 become at the sending end. So to get the voltage and the current at the sending end, we will just replace the x at the equation 4.6 and 4.7 to L, and we get the equation 4.8 and 4.9. The following relationship below, or the equation 4.10, are often useful in numerical computation involving 4.6 and 4.9. That's all. Thank you.